Hello. In this video, we are going to continue the previous example on how to simulate steel plate using Autodyn. This is our steel plate. I created it using design modeler, 1 meter by 1 meter and thickness of 1 centimeter. And this is how I transferred the geometry from static structural to Autodyn. I have a previous video illustrating this process. I'll leave the link in the comments. So now when we open the Autodyn 3D from Workbench, we have our model here. And the plot menu, we can find all these properties and options. We will see the axes to get the right dimensions. So it is 1000 millimeter in X direction, 1000 millimeter in Y direction. If you want to rotate, just click on the left click and still clicking and move. If you wanna move, not translate, just choose this sign. And if you wanna choose a grid or meshing, here you are from grid. Now we will close this. First of all, we will define our materials. So here is the default material structural steel from Workbench, and we will add air and the explosive, which is TNT. Now, this material is from the Workbench, so it is elastic steel, not supporting plastic deformations or plastic model. So we need to modify the properties of the steel to be of plastic model. So our strength model will be Johnson Cook. And these parameters, there are many papers illustrate these parameters based on experimental work, but I am using mine. The strength model for Johnson Cook differs from the elastic simulation uh, in order to obtain beyond the elastic deformation. And if you want to define the material properly, you need to put the failure criteria. We are using plastic strain failure criteria, and we have the ultimate strain for steel structures around 20%, and we'll make the erosion same, plastic strain, and 0.2. And if you want to illustrate if there is cutoff or something, you can put the cutoff maximum expansion, anything higher than the erosion. So we can make it 0.25. And like what I said, there are many papers illustrating these specific parameters from previous experimental work. Now we'll define our domain. The domain will be represented by Euler 3D multi-material. And now our origin of this steel plate is 0, 0, 0. We need to make a previous area from each direction in order to allow the path of the pressure waves expansion. So we'll put x origin minus 100, which is 10 centimeters. Y, the bottom in the Y origin will represent the ground, so we'll not use any special distance from the negative Y axis. So Z will be anything, let's say 1000, which is 1 meter. So dx will represent the width of the plate and the area before and the area after, which make it 1200 millimeters, because we have already 100 in the negative direction and 100 will be after the plate. and dy, let's say 100, 1100, and dx, let's say 3000. So now we're gonna divide our cell, which is the meshing. This is a very important in large experiments and need to be more accurate and make sensitive analysis. So for now, we'll make each is the maximum element size is 1 centimeter. So in the x direction, we will have 120, the y direction 110, and z direction 300. This makes elements of around 4 million elements. So next, we will fill this domain by air and the internal energy 2.068 e to the power 5. Take some time to fill the domain by this huge number of elements and nodes. Now here is our domain. We can check our steel plate position. We can get here and press this arrow and make transparency. So this is our plate and this is our domain. We're gonna insert our explosive material from parts. We'll press domain, then fill, and then additional fill options, data file, read data file. This is our explosion, which was representing 10 kilometers of TNT, like what we did in the previous video. And we choose our origin. So we intended in the last video to make our standoff distance is 1 meter. And now we need to make this explosion at the center of the steel plate, but at a standoff distance of 1 meter. So we'll make X origin 500 and Y origin 500 and Z will be 1000. And we select all materials to remap, then press OK. We find here processing for plans. I choose here x-axis, so the processing in I plane can choose anything because this is a sphere, so it doesn't matter. It will be of great importance if you make a cylindrical explosion, not a spherical explosion. Until filling is complete, we can speak about boundary conditions. Now we are inserting our explosive material in the middle or at the specific coordinate as we intend to simulate. And we expect that it will flow out through air domain, but it will be reflected in the ground, in the base plane, this base plane. So when we'll make now our boundaries, we will make a flow out boundaries in all directions here and here and here and the other side here and here, but not the base plane to allow reflection, which means proper simulation of the experiment. One more thing, we can put our gauges or strain gauge, pressure gauge, uh, any place in the air or on the steel plate to calculate whatever we want. So if we put like pressure gauges behind the steel plate, we can calculate the pressure behind the steel plate and see what is the value of the generated pressure waves and the reflected pressure waves behind the steel plate. And we can put any gauge at any element on the steel plate and calculate von Mises stresses, strain, displacement, whatever. Now we have our fill completed. So we found here our vectors. We can press the vectors to show, and this is our vectors. It is just before the steel plate. Don't forget to put our detonator as a point at the center of the vectors, which is 500, 500, 1000. Now we'll turn off the vectors. Now we'll define the boundaries. As I said, we are making flow out boundaries. The type is flow out. And from here we use Euler and preferred material all equal. Parts, boundary. Take care to be pressing this domain. So block. We will make now from I 1 to 1. This is I plane number 1. This is I plane number 121. If we're gonna plot our boundaries here, we can see these are the fixations for the steel plate. If you wanna show our flow, these are our boundaries for I1 and for I121. We'll continue. Block 111. We will not make for J equal 1 because we expect reflection. So we'll leave this alone. We'll make for the Z directions. So 301. And the last plane is 1. So we have now made our boundaries. So we'll stop spraying them. We want to put our pressure gauge. So I am intending to have my pressure values just behind the steel plate. Let's say 500 and 500 and minus 1000. I have the red pressure gauge which represents the pressure gauge. This one will obtain pressure gauges or energies. If we choose this solid and we'll put 500, 500 and 0, we now have a blue gauge which will be valid for stresses and strains and displacement of the steel plate. So now after that we gonna make join. We don't have except only one element, so or sorry, one particle. So there is no need to merge, but you'll use this menu if you have many particles and elements. Now interaction. This interaction represents the relation between air and steel and how they act and how to transfer from the Euler nodes to Lagrange nodes. So we'll choose it as fully coupled and the Lagrange shell interaction as fully auto. After that, parallel. Here, this is if you have a workstation with full license, you can get benefits from active parallel processing. Now controls, you will get cycle limits as a very high number of limits and the time limit 5 milliseconds and the energy reference cycle same high number of cycles. And now this is how to save and show your outputs from 0 to 5. I need time step of 0.01 milliseconds and the history time 5, and I'm going to select variables that I need to show in my output result file. These are default outputs. I'm going to increase the displacement in 3 directions and the displacement absolute. Now, if I want to disappear this domain, I'll just press none. And if I want to show the contour output for pressure, for displacement, or anything, just choose from this menu. And I'm going to start simulation. Takes some time. This is the recommendation of time step. Use the default settings. And we can see here that start solution and cycles will continue counting until the time step here will be 5 milliseconds here, or there will be failure in the steel bit. It will stop on failure. Thank you. I'm waiting to get one cycle. By the way, is time step multiplied by e minus 4. This is not so bad. More than this, e minus 5 or 6 or 7, it will take months to get your required results. Thank you.